Again, shear stress is force divided by area, so that hasn't changed. What do we call the shear strain? Well, to illustrate that, I have a little drawing right here. Let's say we have a big block of some sort of material. Let's say that we anchor one part of it down on the ground like here. We nail like a 2x4 down here so that this can't move. And now we go ahead and push on the material in this direction. Well, what will happen is this material will deform. And how it will deform is that this top portion of it will be pushed to the right, and because the bottom portion here cannot move, it'll stay in place, and what we find is that this will deform like this, and the material will, in a way, bend kind of like this. I'm hoping that becomes clear. My drawing skills aren't the greatest, but you can see that the top portion of the material has moved over a distance like this, and let's call this distance, let's say, call it delta x. A certain amount of deformation of the top portion of material where the bottom portion of material is not deformed at all. And of course, it does depend upon the height, h here. If this height is very small, then delta x will probably be very small as well. If h is very large, then delta x could be proportionally much larger as well. And of course, the amount that the material deforms like that will depend upon what we call the shear modulus, which is the strength of the material in this particular fashion. So, therefore, the shear strain can now be defined as, and you've probably guessed it, the amount of deformation in this direction right here as a function of the height of the material. So this will be delta x divided by h. And this here is the ratio of shear stress divided by shear strain, which is defined by the strength of the material as being called the shear modulus. So we're going to call this equal to S.